Welcome to the lecture on dynamic vibration absorber. Today we will discuss the damped dynamic vibration absorber. So, in previous lectures we discussed about the theory of the dynamic vibration absorber, and we discussed that dynamic vibration absorber is an auxiliary system that is attached to the main system. So, the main system is subjected to some harmonic force, and therefore, the main system vibrates with certain amplitude. Now, when we attach the vibration absorber system, then the objective is to reduce the vibration of the main system, although the absorber system will keep vibrating. So, in that case, when we used undamped vibration absorber, when it was just a spring mass system, and we saw that due to proper design of the vibration absorber, that is the proper selection of stiffness and mass of the vibration absorber, we can bring the main system vibrations to 0, and that was the role of that undamped vibration absorber. Now, the problem with undamped vibration absorber is that it works at only a particular frequency, because it is tuned at that frequency. Moreover, we can see that when we introduce a dynamic vibration absorber, then the system resonant frequencies, because system becomes 2-degree system, and therefore, it has 2 natural frequencies. So, these 2 natural frequencies, for example, if we have earlier omega by omega 2 equal to 1, now we have at 0.8 and 1.25. So, these are the 2 natural frequencies, and we can see that when we start any machine, it starts from some low speed and it reaches to its operating speed. Therefore, if it passes through the lower resonant frequency of the system, for example, here if it passes through 0.8, although its operating frequency is here, but it has to pass through this frequency. So, at this frequency the amplitude of vibration are quite high, quite large, and therefore, this we can also see from here that without absorber we have here at omega equal to omega by omega 1 equal to 1, we have this peak without absorber. When we introduce the absorber, we have these 2 peaks. So, this with absorber here and here. So, therefore, when we start a machine from low speed to reach to that omega by omega 1 equal to 1, it will pass through this, in this case 0.9, and in the other case here in this diagram 0.8. So, it will pass from the lower resonant frequency, and therefore, at those frequencies the vibration amplitude will be quite high, and the undamped vibration absorber will be able to control this amplitude. Therefore, we will introduce some damping, and therefore the vibration absorber will be called as damped vibration absorber. So here we can see there is a machine and that is supported on some isolator, and the stiffness is K because these two springs are in parallel. So the equivalent stiffness is K1, and we are attaching an auxiliary system, that is the vibration absorber, damped vibration absorber K2, C2 and M2. So here we have one more damping parameter, and so this system we have to study. So this machine is we can, this machine and damper absorber system we can make like, so we have this so we have this support, and this is the stiffness of the isolator of the machine, and this is the mass of the machine. So this is K1 and this is M1, and from this mass we are attaching the vibration absorber, damped vibration absorber. So we have this spring and then this damper, and then this is the mass of the absorber. So it is M2, this is K2 and this is C2, and here we are applying some load on the main mass, that is F0 sine omega t, and the displacement we are taking positive downside, so it is x1 x2 here. So that system is represented like this, because now we will go to write the equations of motion applying the free body diagram and Newton's law. So we make the free body diagram for M1. So here we have M1. Now when we are pulling, so this is the direction we are pulling, it will apply outward upward load K1 x1. Now here if we assume x2 is greater than x1, we will have this K2 x2 minus x1, and then due to damper it is C2 x2 dot minus x1 dot. So this is the spring force due to K2 and damping force, and then there is one F0, the applied force. Now when we make the diagram of M2, so it will have the same C2 and K2, these two forces, but in the upward direction. So here we have shown the free body diagram of this 2 degree of freedom system, where the vibration absorber contains some damping C2. Now to write the equations of motion, we have to apply the Newton's law, that is sigma f equal to m x double dot. So for the first mass, the main mass, we have m1 x1 double dot equal to, so the forces, that is minus k1 x1 plus k2 x2 minus x1 plus c2 x2 dot minus x1 dot, and then plus f0 sine omega t. Now we can adjust these terms. So we can write m1 x1 double dot plus k1. So we take the other side. So k1 plus k2 x1 plus c2 x1 dot minus k2 x2 minus c2 x2 dot, that is equal to f0 sine omega t. So this is let's say question number 1. So now we write for the second mass the equation of motion. So for m2 we will write m2 x2 double dot equal to the forces they are upward, so they will be opposite to the x2 double dot, so they will be minus, so minus k2 x2 minus x1 minus c2 x2 dot minus x1 dot. So now we can write m2 x2 double dot plus, so here we have k2 x2 plus c2 x2 dot equal to, so we can have here minus k2 x1 and this is minus c2 x1 dot, that is equal to 0. This is equation number 2. So we have obtained the equations of motion for the both masses. Now we have to solve this equation. So we assume some solution. So let's say that x1 equal to x1 e power I omega t in the steady state solution. So these are the steady state solution. So x1 equal to x1 and x2 equal to x2 e power I omega t. So because here frequency is omega and amplitude is x1, and here for x2 it is amplitude is capital X2 and frequency is the same omega, because they are in steady state, so they will vibrate with the same frequency as the applied force. So now we have, if we write x1 dot, that is equal to, so we can differentiate it, so I omega into x1 e I omega t, so that is I omega into x1, and similarly here x2 dot equal to I omega x2 e power I omega t, because the differentiation of E theta is E theta, and there is this term the theta I omega. So now this is equal to I omega x2. So a small x is the motion, that is function of time here, and this is function of time, and x2 is the amplitude. So here we are writing now x1 double dot, that is if we differentiate this again, so it will be I omega whole square into x1 e power I omega t. So this we can write I square is minus 1, because I is imaginary, this number under root minus 1. So we can write it minus, so I minus omega square, and x1 e I omega t is again x1. So we can write here x1, and similarly here x2 double dot equal to I omega square into x2 e power I omega t, and so we can write minus omega square and x2. Now we have x1 x1 dot and x1 double dot. Now we can put these values of x1 x1 dot and x1 double dot in these two equations, and we can find the x1 and x2. So now if we put in these equations, so let's first we put here in equation number 2. So we will have here m2 x2 double dot is minus omega square x2. So it is minus omega square x2 plus k2 x2. So plus k2 x2 plus c2 x2 dot. So c2 x2 dot, we have c2 into x2 dot is I omega x2, I omega x2, and here minus k1 x1 and minus c2 x1 dot is I omega x1, so minus c2 I omega x1, that is equal to 0. So we can write here k2 minus m2 omega square plus I c2 omega x2, that is equal to k1 plus I c2 omega x1. Now we can express x2 in terms of x1. So x2 equal to k1 plus I omega c2 upon k2 minus m2 omega square plus I omega c2 x1. So this is equation number 3. So we find x2 in terms of x1. Now we put the same these values x1 dot x1 double dot in equation number 1. So we can have, so m1 x1 double dot, it will be minus m1 omega square, because x1 double dot is minus omega square x1 plus k1 plus k2 x1 plus, so here I omega c2 x1 and minus k2 x2 minus I omega c2 x2 equal to f0 sin omega t. Okay, so we have written this. Now we have to write the equations in terms of x1 and x2. So we can have k1 minus m1 omega square plus k2. So k1 minus m1 omega square plus k2 plus I omega c2, and this is x1 minus k2 plus I omega c2 x2 equal to f0 sin omega t. So we can have, now we can put x2 from here, so it will, this equation will come in terms of x1. So here we have k1 minus m1 omega square plus k2 plus I omega c2 x1 minus k2 plus I omega c2. Now x2 we can put these terms, so it is k1 plus I omega c2 upon this term, so it is k2 minus m2 omega square plus I omega c2 into x1, that is equal to f0 sin omega t. So now we can multiply these terms. So we multiply here this term, so we will get, so k1 minus m1 omega square plus k2 plus I omega c2, and we multiply this term, so it is k2 minus m2 omega square plus I omega c2, okay, minus, so x1 we can take out, so this is k2 plus I omega c2 into k1 plus I omega c2, that is equal to, so f0 sin omega t into this term will go here, so we have k2 minus m2 omega square plus I omega c2, so this term will multiply here by x1. x1 we can bring for in the denominator, later we will take the other side. Now we multiply it, so we multiply k1 minus m1 omega square into k2 minus m2 omega square so we will have k1 minus m1 omega square and k2 minus m2 omega square plus I omega c2 into k1 minus m1 omega square. So we multiply k1 minus m1 omega square with this and this. Now we have to multiply these terms with these terms. So we multiply with k2, so it is plus k2 square minus k2 m2 omega square plus I omega c2 k2. Now we multiply with this, so it is plus I omega c2 k2 minus I omega c2 m2 omega square, or and here plus I square omega square c2 square. So I square is minus 1, I square is minus 1, so here we can write minus omega square c2 square. So this is only the left hand side term. Now we can open this one. So we can open this. So I omega c2 k1 minus I omega. So we can collect the I omega c2 terms here. So here k1 minus m1 omega square, k2 minus m2 omega square plus so here we have minus k2 m2 omega square plus I omega c2 terms. So I omega c2 terms here is k1 minus m1 omega square now we have this term also. So we can write here, so minus, so here k2 k1 and minus k2 into I omega c2 minus, so here minus k2 k1 and minus, then here minus I omega c2 k1 and then it is plus minus I square, so it is plus omega square c2. So we can represent that system in this form. So we have this machine M1 that is supported with some spring K1, and we can have the vibration absorber that is K2 sent to C2 and M2. Now we have to write the equation of motion, and so we have to make the free body diagram, and therefore we make the free body diagram. So here we have M1 and we assume this direction is positive, so we have, if we pull it downward, so it will apply a force K1 x1. Then here there is a spring force. If we assume x2 is greater than x1, so it is k2 x2 minus x1, and here the damping force c2 x2 dot minus x1 dot, and there is also one force f0 sine omega t. So the external force that is working. Now for m2 we can have the same forces but in the opposite direction, the k2 due to the spring k2 and damper c2, and this is the direction of x2 double dot. So we have made the free body diagram. Now we can write the equation of motion. So we can have sigma f equal to m x double dot. So for the first mass we can write m1 x1 double dot equal to, we have the forces minus k1 x1 because this is opposite to the x1 double dot. Now we have plus k2 x2 minus x1 plus c2 x2 dot minus x1 dot, and then plus f0 sine omega t, the external force. Now we can readjust the terms. So m1 x1 double dot, and we have plus k1 plus k2 x1, and then plus c2 x1 dot, then minus k2 x2 minus c2 x2 dot, that equal to f0 sine omega t. So this is equation number 1. So we have this equation of motion for this first mass. Now the second mass m2, that is the absorber mass, we can write the equation of motion. So for this we have m2 x2 double dot equal to, the forces they are opposite, so minus k2 x2 minus x1 minus c2 x2 dot minus x1 dot. So we can adjust these terms. So m2 x2 double dot plus k2 x2 plus c2 x2 dot minus k2 x1 minus c2 x1 dot equal to 0. So this is equation number 2. So now we need to solve these two equations to find the values of x1 and x2. So we assume some solution. So the steady state solution, we assume that x1 t equal to x1 e power I omega t and x2 t equal to x2 e power I omega t. So we assume that the solution will have the amplitude capital X1 and frequency omega, and the second mass will have the amplitude x2 and frequency omega. Now we find x1 dot, so we differentiate this with respect to time. So we will get I omega x1 e power I omega t. So I omega and x1 e power I omega t is this x1, so x1. Similarly here x2 dot equal to I omega x2 e power I omega t, and so we here I omega and x2 e power I omega t is x2, so we can write x2. Now to find x1 double dot, so x1 double dot equal to, we can differentiate x1 dot. So if we differentiate this again, this is I omega square and x1 e power I omega t. So this will be I square is minus 1, so it is minus omega square, and x1 e I omega t is x1, so we can write x1, and here x2 double dot equal to I omega square x2 e power I omega t, so that is minus omega square, x2 e I omega t is x2, so x2. Now we can put these values of x1 x1 dot, x1 double dot, and x2 x2 dot and x2 double dot in equations 1 and 2, and we can solve for x1 and x2. So if we put, so let's put it, so here so now we put the values in equation 2. So here we will have m2 x2 double dot, so x2 double dot is minus omega square x2, so m2 minus omega square x2 plus k2 x2 plus c2 x2 dot, x2 dot is I omega x2, so I omega c2 x2, then minus k2 x1, so x1 is x1, and then minus c2, so x1 dot is I omega x1, so we will have I omega c2 x1, so I omega x1, so we will minus I omega c2 x1, that is equal to 0. So we can write this equation as k2 minus m2 omega square plus I omega c2 x2 equal to k2 plus I omega c2 x1. So we can write x2 equal to k2 plus I omega c2 upon k2 minus m2 omega square plus I omega c2 x1. That is equation number 3. So we have got the expression of x2 in terms of x1. Now we put these values of x1 x1 dot and x1 double dot, x2 x2 dot and this in equation number 1. So we will have here minus, so m1 x1 double dot, so x1 double dot is minus omega square x1, So minus omega square m1 x1 plus k1 plus k2 x1 plus c2 x1 dot. X1 dot is I omega x1, so it is plus c2, so it is I omega c2 x1 and then minus k2 x2, so it is minus k2 x2 and minus c2 x2 dot. X2 dot is I omega x2, so it is minus I omega c2 x2 and that is equal to f0 sine omega t. So now we can rewrite these terms. So we can write k1 minus m1 omega square x1. So this is k1 minus m1 omega square plus k2 plus I omega c2 and this is x1 and then minus k2 plus I omega c2 x2 that is equal to f0 sine omega t. So this is equation number 4. Now we can solve these two equations because they are the unknown x1 and x2, so we can solve them. So we put the value of x2 in terms of x1 in equation 4. So here k1 minus m1 omega square plus k2 plus I omega c2 x1 minus here k2 plus I omega c2 into x2. So if we put these values, so k2 plus I omega c2 whole square, because here we have this term, so it will be multiplied, and denominator term k2 minus m2 omega square plus I omega c2 into x1 equal to f0 sine omega t. Now we multiply this denominator term here and here and here. So we will have k1 minus m1 omega square plus k2 plus I omega c2 into k2 minus m2 omega square plus I omega c2 minus k2 plus I omega c2 whole square, and this is equal to equal to f0 sin omega t into, so this term will multiply here, so k2 minus m2 omega square plus I omega c2, and we can take for a moment x1 here, so that we can solve this left side and then we can write x1 in terms of these functions and these parameters. So we multiply this, so we will have k1 minus m1 omega square into k2 minus m2 omega square plus k1 minus m1 omega square into I omega c2. So we multiply this with this term and this term. Now we multiply these terms to these terms, so plus k2 we multiply k2 square minus k2 m2 omega square plus I omega c2 k2, and here I omega c2 will multiply then the all terms, so I omega, so k2 square minus k2 m2 omega square plus I omega c2 k2. Now we multiply this term to all, so this is plus I omega c2 k2 minus I omega c2 m2 omega square, and then I omega c2 whole square. So this is plus I omega c2 whole square, because this is multiplied with this term, then minus, so minus this square, so it is k2 square minus I omega c2 whole square and minus 2 k2 I omega c2. So this is just left hand side terms. Now we can see k2 square here plus and here minus, they will cancel out. Here I omega c2 k2 and I omega c2 k2, they are 2 I omega c2 k2, and here it is 2 I omega c2 k2 in minus, so these two terms will cancel out with this term. Moreover, I omega c2 whole square plus and I omega c2 whole square minus, they will also cancel out. So now we can rewrite this, so k1 minus m1 omega square, k2 minus m2 omega square minus k2 m2 omega square plus I omega c2. So I omega c2 we have k1 minus m1 omega square and then m2 omega square minus m2 omega square, because we can take this out. So this is the left hand side, and that is equal to f0 sin omega t into k2 minus m2 omega square plus I omega c2 by x1. So now we can write x1, so we can write here So from here we can write x1. So x1 t equal to, so we can write x1 equal to k2 minus m2 omega square plus I omega c2 into f0 sine omega t by this term. So this is k1 minus m1 omega square into k2 minus m2 omega square minus k2 m2 omega square plus I omega c2 k1 minus m1 omega square minus m2 omega square. So we have got x1. Okay, so we have got x1, and from this equation 3 we can get x2. Now the amplitude x1 equal to, we have the mod of this, so that is we have only this term. So we have x1 equal to this term. Okay, so this is the amplitude x1. So we have obtained the amplitude x1 equal to this expression. Now we can define some parameters. So these parameters we can define like mass ratio, m2 by m1 and delta st and omega a square, omega n square, f, g and cc and zeta, and we can express these equations in these terms. So we can write the same equation of x1 in terms of these parameters, that is mu is the mass ratio, m2 by m1, m2 is the mass of absorber and m1 is the mass of the main system. Then static deflection, that is f0 by k1, and omega a the absorber natural frequency, that is k2 by m2, omega n is the main function's natural frequency, that is root k1 by m1, f is the ratio of natural frequency of absorber and the main system, g is the forced frequency by the main system frequency, cc is the critical damping constant 2m2 omega n, and zeta is c2 by cc. So we can write these equations x1 by delta st and x2 by delta st. And here we can, for some given mass ratio 1 by 20 and f equal to 1, we can see that for zeta equal to, so this is this equation is plotted for zeta equal to infinite and zeta equal to 0. So we see that the for zeta equal to infinite, x1 is again infinite and corresponding g is 0.9759. Okay. So it means the for zero damping the x1 is infinite, because without zero damping mean there is no any damping in the system, and we are getting these natural resonant frequencies. And when we put the very high damping, that is zeta equal to infinite, we are getting shift in the natural frequency, and again the x1 is very high. For other frequencies between 0 and infinite, we will get some minimum amplitude. So, this damped absorber will, for certain values of damping between 0 and infinite, will give some finite values of the amplitude of x1. For example, here for zeta equal to 0.1, it is plotted, and we can see that it is giving some reduction in the amplitude of x1. Okay. So, we see that the damped vibration absorber, for certain value of damping, it can reduce the amplitude from infinite to some finite value. And so, I stop here, and we will discuss more in the next lecture. See you in the next lecture. Thank you.